Hello everyone, my name is Chris A. Vance, and in this lesson we're going to see if we can teach you the wonderful world of IPv4 subnetting and VLSM in 20 minutes. So let's get to it. Again, my name is Chris A. Vance. I'm the principal instructor at Wi-Fi Training, and we also have another training group called Rockstar Training. And if you want to contact me about this or any other things, you can visit me at these places. This is me, by the way, so hello everybody. And that is my personal blog, Twitter, the company site, and then my LinkedIn. All right, so why do we subnet? Here's the thing. Larger broadcast domains are a problem. So anytime we send a frame from one host to another on a network, or a packet from one host to another on a network, we start off by having to figure out about that host. So we do like ARP, and we also send other types of broadcast traffic. And if there's nothing containing broadcast and we have really large networks, then it becomes a very poor performing network and we have lots of potential problems. So we don't have any kind of hierarchical structure. It's hard to implement security. It's hard to implement QoS. So we need smaller, more manageable, higher performing networks. The way we do this is by utilizing subnets and things like VLANs at layer 2. Each unique VLAN would then be a unique broadcast domain, which then would require a unique subnet. But also because some of our IP space is really large and we want to subnet it down to smaller segments, that way we're not using it all at once. We need to create more networks for things. There's a lot of reasons to do this. It's easier to implement QoS and it's easier to implement security. So we want to subnet in 20 minutes. I don't know why I wrote 10 there, but we want to subnet in 20 minutes. So here's the thing. There's 3 classes of IP addresses. If you haven't heard about the classes of addresses before, well, here they are. Okay. Class A addresses begin with the first octet value of 0 through 126, and the Class B addresses begin with the first octet value of 128 through 191, and Class C addresses begin with the first octet value of 192 through 223. Now, what's an octet? Well, an IP address actually has 32-bit binary address, and each IP address also has what's called a subnet mask, which is a 32-bit binary address. The binary address is broken up into 4 octets. So these 4 octets allow us to represent that binary value in a decimal format. So instead of writing 32 bits of binary whenever you put in an IP address somewhere, you can write 10, 1, 1, 220. And basically, the computer understands that. But with every IP address, there's a network portion, meaning a portion of that address that belongs to the network, and there's a host portion, a portion which belongs to the host. So if you see a network address like, let's just say 120.64.36.70, there's a portion of this address that belongs to the network and a portion that belongs to the host. What defines that portion that belongs to the network is called the subnet mask. Okay, subnet mask variable is written just like this, and we use the powers of 2 extensively on both the IP address and the mask field. So let's say that this has a /25 address. Well, that would mean that 25 bits are on consecutively in the subnet mask field. Now, each octet, we use the powers of 2. There's 4 octets, and it repeats itself. So 1 power of 2 is 2. 4, 8, 16, 32, 64, and 128. If I were to turn on 1 octet, turn all bits on in the mask field, that would give us a total possible value of 255. Okay? Now, it could also be 0. So if you add all those up, that's a potential value of 256 possible addresses per octet, and there's 4 of them. Okay? And again, the classes of addresses based on the first octet addresses there in the IP address field. Okay, so if you see an address that begins with 0 through 126, the default class for that would be 255.0.0.0. If we were to use an address with this mask and this first octet, that would give us over 16.5 million potential addresses for host. I mean, that's a huge network, okay? That's a huge network. Even Class B addresses is over 65,000 host addresses with a Class B address. And a Class C address is even 254 addresses roughly. So, or exactly. So that's a lot of addresses, and sometimes we need smaller, more manageable performing networks, or we need to conserve addresses. So we need to understand VLSM and how subnetting works. In short, what we were doing is we were taking a classful address, what was a classful address, and we were borrowing bits from the host portion. So let's go ahead and take an example here, 192.168.10.0. Let's say our boss gave us this, and they said we have a /24 to work with. Okay, that's 24 bits on in the mask field. We'll just turn all these on real quick. Just count up to 24. First octet's 8. Okay, and I know the lines are off. I'm trying to rush to keep us in our time of 20 minutes. And I keep we now have, we know that 192.168.10. So if we were to turn that on, 192 is 128 plus 64. And then 168 is 128 plus 32 is 160 plus 8 is 168. And then 10, of course, is 8 and 2 is on. The rest of these values would be zeros, okay? And then we have a 0 fourth octet. Now, let's say your boss comes in and says, this is the IP address space you have, and I need 2 networks created for 10 hosts each, right? Well, I only have 1 address space there he gave me, and he needs a network created for 10 hosts each. So I have to make 2 networks out of this 1 network address space. Here's what I do. We borrow a bit from the host portion. And what that does is that creates 2 networks of half the size. I use a process called NHB, which abbreviates for network, host, and broadcast. What you do with NHB is you always start with 0 for the network address, and then you multiply by the powers of 2 your block size. Now your block size is figured out by subtracting the 256 from your mask value. So if we borrowed 1 bit here in the 4th octet, we would take 256 minus 128, and that gives us 128. Okay, so with that block size, we know we have 2 networks of half the size, so that would be 0 or 128. Now, the broadcast address is another required address for networking. It is the last address before my next network. So in this case, it's 127, and in this case, it's 255. Borrowing 1 bit in the 4th octet only gives us 2 networks of half the size each. The usable host range in that is 1 through 126, and we've got 129 through 254. But I do now have 2 networks that can solve that challenge for my boss. So if I gave this router an IP address of 192.168.10.1 and /25 now, because my mask value would be .128 instead of 255, 255, 255, we borrow that 1 bit, which means that is on, and that's 128. The next network is again that 128, so I could give this router interface an address of 129. That's the first usable address in that network. Okay. Now, there's 2 required addresses that every network must have. Okay, and again, he has a mask of 128 or /25. There's 2 network addresses, there's 2 addresses that every network must have in order to function, and that is a network address and a broadcast address. Okay, so whatever math you come up with, there's always 2 addresses that are going to be reserved: a network address and a broadcast address. Network addresses, here's the rules. Network addresses are always even. Broadcast addresses are always odd. Okay, so keep that in mind as you're learning these things. Let's continue forward to keep up with our time here. So answers we seek from VLSM and subnetting. Which network do I belong to? Which other hosts can I communicate with? How many hosts can my subnet support? And also, am I a valid address? For example, if we were to take that last example and we had an address of .0 with a /24-bit mask, 0 is not a valid address. That is a network address. Okay, so let's take another example here. We're going to use this time 192.168. We'll use .20 this time, and we're going to do .120 as the host value. Okay, and we're going to do a /26 this time. So what do we do with the /26? Well, that's 26 bits on. We know we're in the 4th octet with that because 8, 16, 24, 25, 26. So we know that's the 4th octet value. So let's focus on the 4th octet. we know 120 is on. So 64 plus 32 is 96. And 96 plus, let's see, that's 112, 112 with that on. And then 120. So there's our value for the binary value for that fourth octet. So if we turn that on down here, 64, 32, 16, and 8 are on, that equals our 120 address. Turn all those off, and we know that these two are on. What really happens, what computers do, guys, is a process called ANDing. And they look at the last value in the mask field and say, that was the last bit turned on. That defines the portion of the network. So everything to the left of the line belongs to the network. Everything to the right of the line belongs to the host. Okay? So here's a quick thing. Whenever you draw your ANDing line at the last bit on in the mask value, whenever you draw your IP and mask in octets like this above each other, okay? Everything to the left belongs to the network, everything to the right belongs to the host, okay? If all bits are off, that's your network address to the right of the line. If all bits are on to the right of the line, that's your broadcast address. So if we turn all bits over here off, that would only leave 64 on. So my network is 20.64, okay, and this address, 192.168.20.64. That's my network address, okay? We're going to say that's the network. All right, my broadcast address could be all bits on. So 64 plus all bits on. 64 plus 32 is 96. That's 112, 120, 124, 126, 127. So 127 is my broadcast. Now, that might have seemed a little excessive to do it this way, but this method right here can be used to do subnetting in any the second, the third, and the fourth octet. I do have a shortcut though for subnetting in the fourth octet that I want you guys to write down and get comfortable with. Okay, so whenever we're subnetting in the fourth octet, let's go ahead and use another example. We're going to do 172.16.30.29. Now notice, and I'm going to do a /28 this time. Notice I did a 172.16 address. Classful, that would have been a mask of /16. So we created a lot of networks here. We've got a /28. We created a whole lot of networks. And that is the number of bits borrowed to the powers of 2. Okay? So we have borrowed 12 bits to the powers of 2. That's how many networks we would have created. All right, now let's figure this out. Again, what we're trying to figure out is who I am, who I can talk to, and what size of network I am, and am I a valid address. So I've got a /28. Okay, so the last octet value we have 29, and we see the mask is 28. So 24 bits are already on, 25, 26, 27, 28, and then let's turn on 29. So 16's on, that would be 24, 28, and then 29. We draw our ANDing line. Everything this way belongs to the network, everything that way belongs to the host. Now, before I answer that, here's the key. I'm going to go ahead and give you a trick for our NHB model. Write down network host broadcast, okay, or just NHB. Draw our line under it for our columns. Now what we're going to do, guys, is take the last bit that was on, which is a block size of 16. We're going to start with 0, and we're going to do 0, 16, 32, okay, and 48. I'm stopping because our host value is 29. So 29 lives somewhere in here. Network. These are all networks, and these would keep going up until we reach 255. Okay, the last address before my next network is my broadcast address. So this would be 15, this would be 31, this would be 47, and so on. 29 lives between 16 and 31. So the host I can communicate with is 17 through 30. If I saw somebody else, let's say I saw this particular IP address here assigned to a host here. They were on a switch, and somebody said these two hosts cannot communicate to each other. And then another host over here had the same network address, okay, so 172.16.30, but they were, let's just say, a 36 host address. Okay, so this host was .36, and they both had the same mask of /28. Well, guess what? They could not speak to each other because they are on different networks. Doesn't matter if they even had a straight through cable or a crossover cable that was connecting those two hosts. They could not speak to each other because they technically live on logically different networks. Okay, We've created smaller networks with fewer hosts each, but we've created more networks. All right, let's continue on. And if any of this is confusing, you can always go back and watch. All right, so here's my cheat sheet for the 4th octet. Too many people get caught up with doing math in different ways. I like to tell my students, write this down before you go take your exam. In fact, commit this to memory, okay? You need to know that if I see a /25, that the mask value for /25 is going to be a 128, okay? So 255, 255, 255.128. And then you're going to create 2 networks that are going to have 126 usable host addresses each. Now, you might say, well, the block size was 128, but remember, every network needs a broadcast address and it needs a network address. Okay, so it's however many number of networks you create minus 2 for a network address and a broadcast address. If you see a /26, the mask value is 192. If you see a /27, it's 224. /28, 240. /29, 248. /30, 252. These are the number of networks you create. Again, the powers of 2, 2, 4, 8, 16, 32, 64, and then usable hosts are going to decline. They're going to be inversely related. The more networks I create, the fewer the hosts, right? So 126 hosts, 62 hosts, 30 hosts, 14 hosts, 6 hosts, and 2 hosts. So you have this down and waiting to solve problems, right? And then I know that if I see a host over here and it's got 10.1.1. Let's just say 1, and he's a /30, and I see another host that is 10.1.1.8, and he's a /30, well, what's the problem with that? Well, there's only 2 usable addresses with the /30, so I can only communicate with 1 and 2, and it's a block size of 4, okay? So the block size with that is 4. So I would do my NHB if I needed to figure this out. And networks would be 0, 4, 8, 12, 16, all the way up to 256, right, or 255. Now, the last address before my next network is a broadcast address, so this would be 3, this would be 7, right? So you can see right away there's another problem. .8 with a /30 is a network address. So that host could not communicate, it would not function properly because you assigned a network address to an interface with a /30 mask, it would not work. In fact, most devices will yell at you and tell you that it's not supported. So this is a great chart to have available so I can quickly correlate the number of hosts that would be available, what mask it would be with that value, and the number of networks that I've created. All right. To subnet in the 2nd and 3rd octets, we're going to do that ANDing line that we started off with. I'm going to give you another problem here. We're going to say this problem is 1.1.4.90. And again, what we're trying to figure out is who can talk to who here. So in the 2nd and 3rd octet, that's all we want to know is who can talk to who. Well, the easy way to do that is look, this 22 gets us to 8, 16, 17, 18, 19, 20, 21, 22. Gets us to the 4th. So we're going to bring this 3rd octet down. This is the 3rd octet. This is the one we're focusing on down here. Okay. And again, we had 16 already on, 17, 18, 19, 20, 21, and 22. All right. Now let's turn on 4. 4 is on. All the rest of these are off. And again, we're in the 3rd octet value. What we're trying to figure out is who can talk to who. Everything this way, we draw our line delineating the network portion and the host portion. So that belongs to the network. Everything else belongs to the host. And then we go, all bits off is the network address. So 4.0 is actually a network. 1.1.4.0 is a network. And then all bits could be on in the host portion. If all bits are on, we've got 4 is already on, 5, 6, 7. So 1.1.7.255 is my broadcast. So any host from 1.1.4.1 through 1.1.7.254 is usable. Now, something that usually tricks people up is what about 1.1.5.0? Is that a usable address? Yes, it is. With a /22-bit mask, that is absolutely a usable address, as well as 5.255. That is absolutely a usable address if you have a /22 mask, okay? Because you're counting up everything in that pool up to the max value, right? That's just a bigger network. How big of a network is that? Well, this is the 3rd octet. We know we have 256 hosts here, so we can kind of count backwards a little bit. we know there's 2 more bits that are turned off. So 256, 512, 1024. So there's 1,024 addresses that can be assigned in this network with a /22-bit mask. Again, that's second and third octet subnetting. With the fourth octet, just use the cheat sheet, do your NHB, and you're rocking and rolling real quick. All right, so to put that in use, because hopefully you have learned a little bit about the subnetting process, the VLSM process, to put that in use, to put it in perspective, our boss gave us a network over here of 192.168.0.0 with a /24-bit mask, and he says, look, here's your topology, make this work, okay? So we're gonna do that. The first thing we're gonna do is say, look, we've got 256 possible hosts, so I know I could support this many users. So we start off by the biggest group possible. So right here, we're gonna use the address 192.168, or sorry, the network 0.0. We're going to use that network, except we're going to borrow some bits. So we're going to do a /25 there. Now /25 in that case, if we do our NHB chart, /25 is going to take up 0 through 127. The next network is 128. Okay, so the next network for this host is going to be 0.128. Okay. And now we need to figure out how many would get us to 55 users. Well, that would be a /26. So a /26, /26. And if we do a /26, we got a block size of 64, which brings us up to 192 over here under the network page. So next network is 192. Yep. So that leaves 191 up here under the broadcast. Okay, so that's how that works. Then we need to take out the 25 users. So it looks like I'm going to have to actually remove this for just a second, just to have room for this. So that was 0.0 /25. Okay, and then down here we're going to do 0.192, and that's going to be /27. So the /27, 32 bits added to this is going to be 224. Okay, so the last network was 223. So 224 is my next network, and 192 through 223 are gone, solving this need. Hopefully this is all making sense to you, but the tricky thing with these problems is it doesn't stop there. You still have to get these point-to-point links configured, and I only need 2 hosts for every point-to-point link. So my next network was .224, and we're going to use a /30. That's a block size of 4, so we're just going to go ahead and create the next networks, 228, and then we're going to do 232, and then 236. And that goes ahead and gives me the next network address. So just using that block size of 4 to solve the rest of these problems. So this could be .228 /30, and this is 232 /30. And now we have all the networks we need to make this topology work. And the cool thing is we could advertise saying that anytime you guys over here need to get to this 192.168.0.0 address /24, you come to me and I will take care of it for you. This is just one example of putting it all in use. So I hope this lesson was quick and informative to you. I think we got in there just at 20 minutes. Might have been a minute or two longer, but we had some introductions and stuff like that. We talk much more about subnetting, VLSM, and a lot of network foundation concepts, and a new program we're releasing called Rockstar Network Foundations. And this was a snippet from that. We go into much more detail about IP and really all network fundamental knowledge that somebody should know for a career in networking and to really interact with other network associates. It will also be extremely vital for anybody that's considering like CCNA certification or Network Plus certification. It's a video-based series with lecture, labs, and videos all in one. And it's a lot more like this about so many things that will help you get those certifications and really help you become a competent engineer. I hope you've enjoyed this section, and if you want to find more, go to wifitraining.com or hit me up on Twitter, Rockstar Wi-Fi, and hope to see you soon.